Hi everyone, so I'm re-recording this video, so it didn't turn out as well as I would have liked earlier in the week, so I figured I'd just re-record it. This one problem, the ice table, maybe do it a little bit more clearly, a little bit more slowly to make sure everyone's on the same page. So what I'm going to do is I'll leave up the PowerPoint slide for now, so I'll read through it, and then I'm going to switch to a Word document so I have more space to write. So this is going to be the same problem that we did do on Monday, so we'll read through that. So it says calculate the equilibrium concentrations of N2O4 and NO2 at 25 degrees C. It's in a vessel that contains an initial concentration for N2O4 of 0.050 molar, and it gives us the equilibrium constant for this reaction at 25 degrees C. Alright, so let's get started on that. So, we'll start by listing just things that we know and what we're trying to find. So I wasn't given too much. I know that my initial concentration of the N2O4 was 0.050 molar. It gave me an equilibrium constant of 4.64 times 10 to the negative third, and we've mentioned before that, oops, let me make that a little bit more neat, that for us, there are no units for equilibrium constants. I've mentioned before, it's because they're derived from units called activity, which are ratios, so they don't have units. So our long story short is Kc doesn't have units for us. It did give us a temperature, but I don't need to write that down. The only time I need to worry about temperature is if I was changing the temperature, and that becomes a lot more complicated. But I know my temperature is constant, and so what am I being asked to find? Specifically, the equilibrium concentration of N2O4 as well as NO2, both at equilibrium. And so you've seen what I've done there, where I've made a distinction between my initial concentrations and my equilibrium concentrations. I was also given a balanced chemical reaction, so just for the sake of space, I'm going to wipe this screen, and then I'm going to start with the balanced chemical reaction at the top. So we had this reaction, N2O4, and I'm leaving out states of matter right now, just for clarity. So there's not too much stuff on the screen to, basically get my point across easier. Anytime I'm looking at equilibrium concentrations, immediately my brain should jump to ice tables. So that's going to be our change in our equilibrium. And so my initial concentration, which was given to me in the problem, was the 0.050 molar of the N2O4. It doesn't specifically state, but it's entirely reasonable, because it's not explicitly stated, that the amount of concentration for NO2 at the start is 0. And so what I need to eventually get to are my equilibrium concentrations. So what I need to do is ask, well, is the reaction going to go forward? Will it go in the reverse? And then how is this going to change? So if I look here, I have nothing in my product side. So there's no way a reverse reaction could even happen, because you can't create something from nothing. So this reaction must be going in the forward direction. And we'll cover more later with something called a reaction quotient. So if numbers appeared on both sides, you'd still be able to figure out if it was going to the forward reaction or to the reverse. Well, since I know the forward reaction is going to progress, I know I'm going to consume some amount of N2O4 and then produce, so plus, some amount of NO2. And it's always going to be in the ratio of 1 to 2. It's not written here, but there's a 1 that's implied there and a 2 that is written explicitly. There's my implied 1, and there's my 2. All it's telling me, again, I'm consuming, as I consume 1 mole of the N2O4, I'm going to be producing in a molar ratio of 2 of my product. How many reactions happen? I don't know, and that's why we still have to solve for X. So if I add up my initial and my change, I'll find that my equilibrium concentration for N2O4 is this. So it's what I started with minus whatever I lost. And then my equilibrium concentration of NO2 will be whatever I started with, which is 0, plus anything that was created. So what I've got to this point is I've technically finished the ice table, but I haven't answered my final question. I have yeah, an expression for the final concentrations of NO2 and N2O4, but what I really need to find is actually a numerical value. I don't want an equation. So when I'm solving for this, right, whether it's NO2, right, when I'm solving for them, I better have a quantitative number, not just an expression. And what I mean by an expression is because I have unknown variables. So what next then? Well, luckily for us, I know I have my reaction quotient, because effectively what I've done here is I have one unknown, but no equation to dump it into. So I got to make that equation to solve for that one unknown. So I can look at my balanced chemical reaction, and from that balanced chemical reaction, I can write the equilibrium constant expression, which will look like this. Oops. And I know that's equal to a value because it was given to me in the problem that this expression must be equal to that number, 4.64 times 10 to the negative third. So what I can do then is start to replace these variables with numbers that I know. So I'll take my top, right? My equilibrium concentration of my products was 2x, and it's going to be raised to the second power. And then if I have my denominator, which is going to be my reactants, that's my 0.050 minus x. And so I end up with this expression here. So this is a little bit different than when we did our first example. I could theoretically take the square root of the right-hand side, and I can do it to the left-hand side as well. It's easy enough to get rid of that square, but there's nothing, you did not make your life more easy this way. You've basically got yourself into a dead end. So that is not going to be the way that we can proceed to solve for x for this problem. So we're going to have to find out a new route on how to do that. So what we're going to need to do is actually put it into quadratic formula, in like the quadratic form. So quadratic form. That's what we need to get it into. And what do I mean by quadratic form? It should look like 0 equals x squared plus x plus, some number. So I want it to look at like in that, this form. So what I'm going to do, because I've run out of space, is I'm going to wipe the screen again and then just recopy what I have on the bottom, so we can just follow the math a little bit better. So we said we had 4.64 times 10 to the negative third, and that equaled 2x squared all over the 0.050 minus x. So I start to do some of the easy math first. Let me just do the numerator. So remember, this square is on the outside of the parentheses. That means both things inside it get squared. So it becomes 4, or 2 squared, x squared. So that's my numerator. And there's not much more I can do down here. Pretty much just carry that over. So let me rewrite it a little bit more neat. And it's getting a little bit squished because of the stylus. Those are 10 to the negative thirds, if you're wondering. Alright. So then my next step is, well, I need to get x somehow, get all the x squareds together and then all the x's together. But I have this, I can't think of the word right now, but everything inside the parentheses, right? I'm going to need to factor that out later. So what I'm going to do is I'm going to multiply both sides of the equation by the denominator. So I've run out of space here, but you'll see what I mean in a second. So what this will turn into, there's my 4.64 times 10 to the negative third, times what used to be on the denominator, equals 4x squared. So now what I need to do is make sure I remember how to factor things. It's foiling, right? If we remember, forget that this goes back to like 7th or 8th grade math, right, or whatever it is. The way I learned it was first, outer, inner, last. And what that tells me is the order in which I should start to multiply my my terms together. Luckily for this one, we don't actually, it's not too much foiling we have to do. We just need to mostly keep track of first and last for this one, because we don't have anything more complicated. If this had another variable in it, like a y or an x, would be in more difficult shape. But this is not bad. We just want to make sure both of these get multiplied. So when I say both, I mean both these terms get multiplied by that first term. So what is this going to look like when I'm done? Let's do that first. So if we multiply the 4.64 times 10 to the negative third by the 0.05, what we should get is 2.32 times 10 to the negative fourth. That was from doing that multiplication. And then my second multiplication is the 4.64 times 10 to the negative third multiplied by negative x. So it becomes minus 4.64 times 10 to the negative third x. And all of that is equal to 4x squared. So I'm starting to see things come together now. There's my x squared term. Here's my x term, and there's just my number term. So I'm actually getting closer to making it look like the quadratic equation. So I'm going to pull everything to the right-hand side, because I'm just used to having my 0 on the left-hand side. So that means I keep the 4x squared, nothing happened there. But I'm going to basically take this term and then put it onto the right-hand side, so it becomes plus 4.64 times 10 to the negative third. Now I'll move this term to the right-hand side, so it becomes a minus 2.32 times 10 to the negative fourth. So now it's set up in a way that I can put it into the quadratic equation where I need to know terms a, b, and c. A is going to be 4. Oops, I missed an x in there. It's an x. Right. A is going to be 4, B is a positive 4.64 times 10 to the negative third, and then C is going to be a negative 2.32 times 10 to the negative fourth. The only reason I specifically mention that is because you're going to need to put this into a quadratic calculator. What do I mean by that? I realize everyone's on the internet when they're taking, you guys are at home. Usually I would have students do the quadratic equation by hand, but it will probably save you a lot of time, and I'm going to, still there will be a, you need to sign something saying you're not cheating, but I will allow you to use the quadratic equation. I'm just using a calculator online. So what I would recommend is finding one before the quiz that you like and get comfortable with it. So we need to dump that into the quadratic equation. Most calculators ask you for A, B, and C, and what they'll do is, because remember, we're looking at a quadratic equation. X's are the ones where the equation will pass through the x-axis. So for most quadratics, you're going to get two numbers. And what I get back by plugging in our information into quadratic calculator is 1x is equal to positive 7.06 times 10 to the negative third, and the other x is equal to negative 0.008. Right off the bat, this has to be wrong, and so we can just toss it out. How do I know that? Because if I look at the balanced chemical reaction, the N2O, N2O2, there we go, going to 2NO2, right? If I started with 0, right, and I'm producing 2x, right? If this were a negative number, that means my equilibrium concentration is somehow going to be a negative number, because I'm plugging the x into that 2x. That makes no physical sense, right? So our rule for our class, oops, I didn't mean to erase everything, so I didn't do that, good, is going to be, if you get a negative number, then that is the one you toss out. And so that won't always be the case, but I'll design the problems so that will be the case. So we have one of our x's that will work, and again, we always have to ask the question, what is x, right? So we remind ourselves, if we go back to our balanced chemical equation again, N2O4, if we're just looking at our equilibrium values, right, we already said the equilibrium concentration of the N2O4 is going to be equal to that, and the equilibrium concentration of NO2 would be equal to that. That's what my X quote-unquote is. That's the number that gets dumped into those two expressions. So let's finish that off. So our final answer, right, if we're looking for the equilibrium concentration of N2O4 and the equilibrium concentration of NO2, 0.050 minus, in my X we said was 7.06 times 10 to the negative third. Then here we know it's going to be 2 times 7.06 times 10 to the negative third. So I'm just checking my notes. Plug everything in. What we should get is 0.043 molar for the N2O4 and the 0.00706 molar for NO2. So hopefully that wasn't too long of a video, but it was slow and methodical. As you get better with these and more practice, you'll get quicker and quicker. You're going to find out there's a lot of patterns that you can follow. All right, so hopefully that was more clear this time. So if you have any questions on that, shoot me an email, and I will see you all on Friday.